Our next topic in statistics is probability. Probability. When we carry any, say, a question in probability, we are going to carry what we call experiment. Therefore, what we do is called an experiment. Then you have the outcome of the experiment. For example, I toss a coin. The outcome is head. This is called outcome. When I throw a die, I got a 5. This 5 is called an outcome. A number of outcomes or one outcome could be called an event. For example, in the tossing of the coin, you're going to get a prize if you get a head. If an event is to get a prize. And how do you get a prize? You have only one outcome, head. In the throwing the die, you will get a prize if you get 5 and 6. Therefore, the event is to get a prize, and the outcomes are 5 and 6. When we put down all possible outcomes, we call this sample space. Therefore, we are going to carry experiments and we are going to talk about events. Now, as I said, all possible outcomes, all possible events is called sample space. In many problems of probability, of course, probability of an event is always less than 1 because the number of times the events happens is less than the total number of times, total number of outcomes. So always probability is less than 1. Probability of an event not happening is 1 minus the probability that the event is happened. Sometimes in problems, maybe we need to show the whole sample space in order to answer our questions. For example, if we have cubical die. Its numbers are from 1, 2, 3, 4, 5, 6. If we have a triangular or tetrahedral die, it will only have 4 faces, 1, 2, 3, 4. If you have one like this, and I ask you that, you are going to throw 2 of them, and then you are going to throw 1 tetrahedral die twice, and we are going to add the scores. Maybe it is possible now that you make this in a table. The first die can show 1, 2, 3, 4. And the second one can show 1, 2, 3, 4. And the event or the outcome is to add the two scores. 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8. Now, if the question is, the event is that the score is 4, what is the probability of 4? We count the number of 4s, 1, 2, 3, out of how many? 16. So we write 3 over 16. If I ask you which event would get the largest probability, you say to me 5, because the 5 occurred 4 times. What is the probability of 5? Then you say 4 over 16. In some problems, you get the answer 1 over 4. In some problems, we may need to show the sample space, and then we choose from it. Another example, if it say that we have, in actual fact, families of 3 children, and we're considering the number of boys and girls, family of 3 children, a family of 3 kids. Then we say, what is the outcome? It could be a boy, 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 or it could be a boy, boy, girl, could be a boy, girl, boy. It could be a girl, boy, boy. It could be a boy, girl, girl, or a girl, boy, girl, or it could be, or a girl, girl, boy, or girl, girl, girl. If I ask you what is the probability of having 2 boys and 1 girl, you are going to count them. This and this and this. It is 3 over 8. Problem like this. Now, one thing we do when there are 2 events happening, that we use sets and we use Venn diagrams. For example, this is the universal set, and this is the event A, and this is the event B. Maybe the event A represent, first of all, we would like to get acquainted with sets. What does this area, right? I call it X. What does this area X represent? It is A intersection B. What does this area Y represent? The area Y represent A intersection B complement. what does this area Z represents? The area Z represents, right? Now, the area Z is B intersection A complement. What does this area T represent? This is A union B complement, or A complement intersection B complement. Therefore, we can use sets. Now, what we are going to put in these squares, either the number of items or its probability, both works. For example, this is a set, item A, item B. Maybe, right, event A, event B. Maybe the number of A intersection B is 5. This area is 15. That area is 20. And that area is 10. Total is 20 and 20, 40, 50. So what I wrote inside each outcome is the number of times it happens. Instead, we can put probability, right? The same thing. And we say this area is 5 over 50. This is 1 over 10. This area is 15 over 50. 15 over 50 is 3 over 10. This area is 20 over 50, 2 over 5. And this is 10 over 50, 1 over 5. Here I put the probability in the corresponding regions. We use this more than this one, in which we put probabilities. Right, let us now consider this. This is a set this is the event A, and this is the event B. Now let us call these areas is X, Y, Z, and these are probabilities, and this is W. Now, if I ask you, what is the probability of A plus the probability of B? I say equal to. A is X plus Y, and B is Y plus Z. So the sum is X plus 2Y plus Z. If I ask what is the probability of A intersection B, right? A intersection A intersection B. The area A intersection B is Y. What is the probability of A union B? Is area X plus Y plus Z. What is the sum of probability of A intersection B plus the probability of A union B? The answer is X plus 2Y plus Z. It is the same answer I got up. Therefore, there's a conclusion that the probability of A plus the probability of B, it is the same as the probability of A union B plus the probability of A intersection B. This is a very important rule, and it is mentioned in the formula sheet, this rule, that the sum of the probabilities, probability of A, probability of B, is the same as probability of A union B plus probability of A intersection B. We could have a question about this, a useful, a nice question about this. Now, we can have the question, this one, which is example 6 in the book. It says the probability of A intersection B, it says the probability of A union B is given to be 0.9, and the probability of A is 0.6, and the probability of B is 0.7. Then we asked to find many things. The first question we want to find is what is the probability of A intersection B. So we say this is equal to probability of A plus probability of B minus the probability of A union B. And the answer is we add 0.6 plus 0.7 minus 0.9, we get 0.4. Once we got this, then we drew the Venn diagram. In the Venn diagram, we have the probabilities. This area 0.4, right? Maybe you better do it in the next page. Now we draw the Venn diagram. This is a set A and the set B. Set A, set B, our event A, event B. This is 0.4. Because the probability of A is 0.6, this area is 0.2. Because the probability of B is 0.7, this area 0.3. And then 0.2, 0.4, 0.6, 0.3, 0.9, this area 0.1. Then we can answer any questions. Like a question say, what is the probability of A complement. 1 minus the probability of A. 1 minus 0.6 equal 0.5. 0.2, 0.46, right, 0.43. 1 minus 0.46, the answer 0.4, which is the same as 0.3 and 0.1. Other question, it say what is the probability of A, right, complement intersection B. A complement intersection B means the area outside A and inside B. The answer is 0.3. Sometimes when you have a question like this one, what is the probability of A dash union B? Sometimes this kind of problem, right, might not be understood by the students. This actually says take all the area outside A plus the area of B. Therefore, this area is included. Why? Because it is inside B. Union means this or this. Anything outside A or inside B. Yeah, and the answer should be this and this and this. There is a better rule to make you understand this. I call it the rule of the complement rule. What you do is, you do this. You write the set and write complement of each one. What is the complement of A? Complement is A. What is the complement of union intersection? What is the complement of B? Is B complement. And then you put a complement outside. Because when we have this question with a complement outside, means we complement each one. Therefore it becomes A complement, complement of intersection union, complement of B complement is B, which is the same as this one. But this is easier. Why? Because when you look at this question, you say, what is the area inside A and outside B? The answer is 0.2. What is the complement of 0.2? Yani 1 minus 0.2. 1 minus 0.2, which is 0.8. Which is something maybe you understand better than union. Intersection, no problem, we understand, yani say easily. But when we come to union, you can convert a union problem into an intersection problem. Fine. Now we are going to go into something new, something we did not take, right, in O-level probability. It is something we call conditional probability. Conditional probability. Conditional probability is represented in questions like this. When I say the probability of A conditional B, this line means condition. The rules say this: the probability of A conditional B equal to ratio of two probabilities. It is the probability of the intersection at the top and the probability of the condition at the bottom. This is logic. Because you say, I want the probability of A in conditional B. You were therefore conditional that you have to belong to set B. Fine. But set B is your total. And then you are going to getting those who are in A as long as B. And this is exactly what we put there. Therefore, the conditional probability is a ratio of two probabilities, not a ratio of two numbers. One probability is the ratio of two numbers. One probability is the number of times the event happened over the total. But the conditional probability is a ratio of two probabilities. The probability of the condition is written down, and the probability of the intersection of the two events in the top. Now, how do you get the wording of conditional probability in questions? Might not say in the question find conditional probability, but you can be given these words, given that, right? When this, or if this happens, or when this will happen. These are all conditional words in questions, implementing or implying that it is a conditional probability. Right. Now, we can have a question here, right, about this. The question is, we take example 8. It says the following. The probability of C is 0.2. The probability of D is 0.6. And the probability of C conditional D is 0.3. What is the meaning of the probability of C conditional D? It means the probability of C intersection D over the probability of D. We substitute numbers, 0.3 equal the probability of C intersection D over the probability of D layer 0.6. This means the probability of C intersection D is 0.18. Then we go and draw the diagram, the Venn diagram. This is the set C, and this is the set D. This area of intersection is 0.18. And the probability of set C is 0.2. Therefore, this area is 0.02. And the probability of set D is 0.6. Therefore, this area is 0.42. And when we add all of this, we subtract from 1, we got this area 0.38. Hence, we can answer any question. Right? The first question we were asked is, what is the probability of D conditional C. It is the probability of D intersection C over the probability of C, which means the intersection is 0.18 divided by the probability of C, which is 0.2. And we get the answer equal 0.9. Another question we could be asked, what is the probability of C complement intersection D? Mean the area outside C inside D, 0.42. We can have a question of probability of, right, C dash intersection D dash. Mean the area outside C and outside D, 0.38. Right. This is what we call conditional probability. Now, you remember we had problems in the O level are solved by tree diagram. We can also have problems here solved by tree diagram. For example, we have here example 10, which it says the following. A turnout, right, of the attendance in a motor rally will depend upon the weather. On a rainy day, the probability that a big attendance, 0.4, but it does not rain, the probability is increased to 0.9. What is the probability that we have? The forecast gives a probability of 0.75 that it will rain. Therefore, it will rain 0.75. It will not rain, we call it R dash, 0.25. If it rains, the probability of big attendance is 0.4. But if it doesn't rain, the probability is 0.9. Big attendance, not a big attendance, 1 minus 0.4, 0.6. Not a big attendance, 1 minus 0.9, 0.1. Then we can answer questions like this. It says here, the first question, that there is a big tournament and it rains. We want the probability of B intersection R. Therefore, this is equal 0.75 times 0.4. That's it. That is the answer. Right, 0.3. Now, then it says another question. There is a big attendance, right? No, the other question, there is a big attendance. Whatever the case, the probability of B. Probability of B means either probability of R and B, 0.75 times 0.4, or R dash and B, 0.25 times 0.9. This is the total right, of the two answers. And this would be equal 0.525. I can add a question here of conditional probability, right? What is it? What is the probability of it rains conditional a big tournament? So we put the probability of B down, and at the top we put the probability of R intersection B, which means the ratio of the two answers, 0.3 over 0.525. Now, we come to a very important point, is that sometimes when we have two events, we may have a case like this, a case like event A alone and event B alone. What does this diagram implies? Imply that the probability of A intersection B is 0. We call this case that the two events are mutually exclusive. We call them mutually exclusive. The two events are mutually exclusive means the happening of one prevent the happening of the other. Whenever we have a case like this, we call it this word, mutually exclusive. So A and B are mutually exclusive. As you can see, no intersection between them. Accordingly, if no intersection means probability of A plus probability of B equal probability of A union B. Because there is no intersection. It is the same as probability of A union B. And this is what we call the addition rule we took in the O-level. The addition rule, that when we say or, we add probability of A union B means the probability of A or B equal probability of A plus the probability of B. This is only true if the two events are mutually exclusive. Means if one happens, the other doesn't happen. Now, if two events are independent, what means this? It means that A and B, so A and B independent It means the happening of A is not affected by the happening of B. A will happen whether B will happen or not, means the probability of A conditional B, it is exactly the same as probability of A, because A will happen whether B will happen or not. What is the rule for A conditional B? It is the probability of A intersection B over probability of B. Therefore, this is exactly equal probability of A. Therefore, what is probability of A intersection B? Equal probability of A times probability of B. We call this, whenever A and B are independent event, the probability of their intersection is the product of their probabilities. For example, we take this example. It says here that, example 14, events A and B are independent. A and B are independent. And the probability of A is 1 over 3. Probability of B is 1 over 5. We want to find what is first, the probability of A intersection B. We say this is equal probability of A times probability of B, which means 1 over 3 times 1 over 5, 1 over 15. What is the probability of A intersection B complement? Then we need to make the draw with the sect. This is A, and this is B. This is A and this is B. Now, this area is 1 over 15. Therefore, what is this area? 1/3 minus 1 over 15. 5 over 15 minus 1 over 15, give us 4 over 15. This area is 1 over 5 minus 1 over 15. 3 over 15, that means 2 over 15. If we add them or subtract, we get this area 8 over 15. Therefore, if you ask what is the probability of A intersection B complement, mean the area inside A, outside B, the answer is 4 over 15. And if we asked another question, what is the probability of A dash intersection B dash, mean the area outside the two sets, which is 8 over 15. Therefore, once or 8 over 50. Once we get the area of intersection Then we can complete the Venn diagram and answer any question. Now, we have one more example. Right. A bag. This is example 16. We have a bag, and the bag contains, right, 7 green, and 5 blue, and a bead is taken from the bag at random. The color is recorded and the bead is replaced. Then a second bead is then taken from the bag and its color is noted. Therefore, this is the first bead. Green, 7/12. Blue, 5/12. The next one will be the same. Why? Because it is replaced. Green, 7/12. Black, 5/12. And the same thing here. Green, 7/12. Black, 5/12. It say find the probability that one bead is green and the other is blue. I want the probability of one green and one blue. Means probability of green and blue plus the probability of blue and green. Right, which means 7/12 times 5/12 plus 5/12 times 7/12, which is the same. We got, right, 35/144 plus 35, gets it at the end, 35/72. Then it says here, show that the event, the first is bead, the first green is bead, and the event, the second green, right, bead is green are independent. You want to show that the first green and the second green, the first green, the second green is independent. In that case, we need to get each probability separately. What is the probability that the first is green? The first is green is 7/12. Then we get the individual probability that the second green means 7/12 times 7/12 plus 5/12 times 7/12. If we add this, we get the answer is we can take 7/12 common factor. Therefore, the answer is, right, 7/12. Right, 7/12. Okay. Now, probability that the second is green is 7/12, yes. What is the product of the probability the first green and second green is 7 over 12 times 7 over 12 times 7 over 12, which is the same as the product of the first green times probability of the second green. Therefore, they are independent. Therefore, the two events are independent. Right? Therefore, we get the probability that the two events are independent. Why? Because the probability of the first green and the second green is the same as the product of the first green alone times the second green alone. It is the same answer, 7 over 12 times 7 over 12. And therefore, if the product of the two probabilities is the same as, right, the probability of the two events happening, then the two events are independent. And this is the end of the topic of probability.